Okay, in this lecture we are continuing our review, and now we are going to discuss in detail the network layer. Actually, we're going to cover some key points that you should have learned in 475 or whatever other bachelor's level networking course you've had in the past if you didn't have 475. Um, So let's take a look at what does a network layer do. Well, basically what it does is it transports segments from a sending to a receiving host. On the sending side, the network layer encapsulates segments into datagrams, and on the receiving side, it delivers segments to the transport layer. Unlike the application transport layer that's really operating um, at the host, at the two end stations, the network layer protocol is actually running and being used not only on individual hosts, but on routers throughout the network as well. And the routers are going to basically examine the header fields in all the IP datagrams and do what we call forwarding. Actually, routers do forwarding and routing, which we will talk about on the next slide. So as I said, there are two key network layer functions that are conducted by the routers in a network, and they're basically related to each other. The first one is forwarding. That's basically moving packets from the input to the appropriate output on the router. So basically by looking at the IP addressing and subnet information, the router is able to look at the IP headers and look at the addressing and determine, where, what output port that the IP packet should be going. The reason it's able to do that is because it has information from the other routers on the network and other networks, because it's basically performed a routing function. It has some routing algorithms, which we're going to talk about later, and it has basically a picture of what the network should look like. So when it receives an individual packet, it knows where to send it. The analogy of routing and forwarding, and they're kind of interrelated with each other. Routing is kind of the big picture. So if we're going to we're in the process of planning a trip, our routing, the analogy of routing would be planning the trip from the beginning to end. Forwarding is basically all the decisions that are made throughout the trip, what road to take, which exit to take, those types of things. So there's basically an interrelationship between the two. So basically, like I said, every router has some sort of routing algorithms. They're basically sending and receiving data from other routers on the network to learn what the network looks like. And based on that information, when these IP packets come in, it reads the header information, reads the IP address, and understands the subnetting involved, and is able to take that input and figure out which output link it's going to send that packet out. And it knows which output link because it knows what networks are available, and it knows what's the fastest path to get to a particular destination, and basically sends that data out that proper output link. Oops, sorry. I'm going to skip this section. So there's basically two types of networks. Networks that have virtual circuits, and we're not going to really cover that. And datagram networks is going to be the function for this particular review. So in a datagram network, unlike a virtual circuit network like an ATM or frame relay network, there's no call setup. And the routers aren't aware of any state about any end-to-end connections. They're just taking in datagrams as it is and forwarding it to the correct destination. It's really up to the higher levels of the in the protocol stack to set up a connection. It just knows it's receiving datagrams, it understands the network, and it knows where to send them. So in your datagram forwarding table, you basically have address ranges or subnets listed rather than individual addresses. Obviously, there's 4 billion IP addresses, so you're not going to have data on every single IP address, but rather each router is aware of different ranges of addresses, and which we usually refer to as IP subnets. And we basically, based on the different address ranges, we send our the IP packets out of different output links. And sometimes we just have a case where we might have one particular port that says, okay, for any other address that's not in this list, we'll send it out this other port. So we don't have to, at each router, have to have information about every single IP address subnet that's out there. Just usually the ones that we deal with relatively locally or that we've learned about, and the rest of them we probably have some other port. We know some other place to send the data. Here is an illustration. We have a datagram forwarding table. Now, basically what we're trying to say here is for this particular address range, we want to go out this interface, and this next one we're going to go out this one, and next one we go out this one. And for any of the addresses that don't fit into these ranges, we're going to go out this third interface. It's kind of a oversimplified way of looking at a network forwarding table, but this kind of illustrates at a very high level what the forwarding table is doing. But what would happen if the ranges don't divide up so nicely? So what we do is use what's called longest prefix matching. So when looking for a forwarding table entry for a given destination address, we use the longest address prefix that matches the destination. So here we have these 3 different address ranges, and we have this one here. This one obviously matches this first one. This one matches the second or third, but if we're going to pick the longest, we're going to pick this address range. And the reason, of course, is basically when we get into subnetting, that's the reason that we pick that longest prefix, because we're basically picking the more distinct subnet. We haven't talked about subnets yet, but we'll get to it shortly. And so here's basically a summary of forwarding and routing that we've just talked about. So in forwarding, we basically look up the address prefix and determine the from a particular input link what output link the data is supposed to go to. And routing is matching the address lookup table and the longest prefix match, because what we're saying is different subnets are going to have different routes, and that's going to determine how we're going to forward those packets. So you see you have an example here where the prefix of these two start off the same, but this is clearly a different subnet than this prefix over here. So these two go to 2 different next hop routers, and that therefore they have to go out two different interfaces. So the next thing I want to focus on in this learning module is the IP protocol. So we want to talk about format of IP, IPv4 addressing, ICMP, and IPv6. So at a very high level, there's a lot going on in the network layer. We basically have both host and router related network functions. We have routing protocols, what we're going to talk about, that allow the router to determine which path to set and to select when routing data or routing packets. And there's different actual routing protocols we're going to discuss later, such as RIP, OSPF, and BGP. There's forwarding, so forwarding tables are built by decisions a router makes with as a result of these routing protocols. And you also have the IP protocol, which basically is the addressing that allows communication throughout the network to occur. And you also have ICMP protocol, which is used both for router signaling and for error reporting throughout the network. So let's take a look at what's inside of the IP, of an IP datagram. So we basically start off with the version number, which is either IPv4 or v6. We have a header length in bytes. We have a type of service, which is basically the type of data, either real versus non-real time. We have the total datagram length in bytes. We have, for the purposes of fragmentation, reassembly, and we'll look at this a little bit later, we have three fields. We have a 16-bit identifier, we have some flags, and we have a fragment offset. We're going to take a look at that later on in the lecture. We have a maximum number of remaining hops, which is also a which is used in routing, and this gets changed every time a packet makes it through a router, so we don't have packets that stay on the network forever. We'll get to that later on as well. We have a designation for the upper layer protocol to deliver a payload to. We'll see an example of this in the Wireshark lab. You have a header checksum. You have the all-important source address and destination address. And you also have some options we'll get to later as well. And finally, you have the data, which is usually a TCP or UDP segment. So basically, you have about 40 bytes of overhead overall. You have 20 in the TCP header and 20 in the IP header, as well as any application layer overhead that you might have before the actual data. So let's talk about the concept of fragmentation and reassembly. So in IP networks, very often we have the concept where we have a very large piece of data that has to be fragmented and then reassembled at the end. So basically, The network links have a maximum size called maximum transmission unit, which is the largest possible link level frame, and this varies based on different link types, have different MTUs. We're gonna see that when we talk about link layer. Basically, as a result, a large IP datagram has to be fragmented to fit within, so we have different fragments that all fit within that MTU, that maximum transmission unit. This causes one datagram to end up becoming several datagrams, and so what we have to do is you have to reassemble them at the final destination. So basically in the IP header, as we mentioned previously, there are some bits that are used to identify in order the related fragments. So as we mentioned previously, there are different fields within the IP header. There's basically the data unit identifier, and that is an ID number in each datagram that the sending host puts inside each IP header. There is the total length, which is the length of the user data plus the header in octets. Then we have the data offset, which is a position of this particular fragment that we have in the original datagram, and this is usually in multiples of 8 octets or 64 bits. Since we need to keep track of whether or not we have reached the end or not, there's a more flag. The more flag indicates that this is not the last fragment. And datagrams can be fragmented and refragmented at any router, and they are only reassembled at the destination host. So all this information in the header is used to identify the related datagrams so they can be later reassembled. So here we have an example. We have a datagram that we want to send that has 4,000 bytes. However, our maximum transmission unit size is 1,500 bytes. So this one large datagram has to be separated into 3 separate datagrams. So the first one has a length of 1,500. It has a particular ID number, and all of these, since they're related, will have the same ID number. Okay, it's going to have a flag of 1, indicating that it's not the last datagram, and it's going to have an offset. Obviously, we start with the offset of 0. Then we have our offset, which for the second datagram, which, if we remember, is going to be in multiples of 64 bits or 8 octets. So we, since we have 1,480 bytes in the data field, the offset for this is going to be that 1,480 divided by 8, which is 185. And then finally we have our last datagram, which is smaller than the previous, since we only have a total of 4,000 bytes. Next up, let's talk about the very important concept of IP addressing.